for the kind introduction. Before I start, I would like to say a few words about the University of Oslo and the work that we are doing in transmission electron microscopy. Basically, all the transmission electron microscopy work is done in the structure physics group, which is, of course, part of the Department of Physics, but also we belong to the Center for Material Science and Nanotechnology, the so-called SMN. This is a bigger umbrella enhancing interdisciplinary collaboration among 5 different research groups in physics and chemistry department. So we are focusing on energy-related materials for sustainable energy solutions, having different directions like in solar cell technology, high power electronics, batteries, hydrogen storage, fuel cells, thermodynamics, and quantum technology. So this is just a simple outline of my talk today. I will start talking about the current needs for new materials for lithium-ion batteries. Then we will move to the material of interest, which is MaxENS, a promising 2D anode material for all solid-state lithium-ion batteries. And then I will give you 2 different examples with TEM. One, how we can use TEM in situ TEM in order to achieve growth of MaxENS and explore their fundamentals of their growth mechanism. And then we will move in operando transmission electron microscopy, showing how we can miniaturize real-life devices. So it is well known that in the past 3 decades, lithium-ion batteries have pervaded almost all portable electronics like smartphones, laptops, tablets, all electric automobile vehicles, and also different segments of the energy storage market as the most reliable rechargeable battery technology. Of course, these activities are in line with the societal needs addressed by the UN Sustainable Development Goals, and in particular, the goals for affordable and clean energy, climate action, industry, and infrastructure. However, the growing global demands for large-scale energy storage and for safer battery technologies have intensified research towards all solid-state lithium-ion batteries. This means that by replacing the flammable organic liquid electrolytes by inorganic solid electrolytes, we can achieve batteries that are chemically safer, compact, faster recharging, and they can operate at higher temperatures. So far, the majority of research efforts have been focused on developing new materials for solid-state electrolytes and cathodes. However, research last years has been intensified towards new promising anode materials after the discovery of MaxENS, a new family of 2-dimensional materials. MaxENS are transition metal carbides, nitrides, or carbonitrides having different mass per formulas, and they exhibit the potential to replace and even supersede the properties of the most common 2D anode material so far, which is graphite. Theoretical calculations so far have showed that MaxENS, of the lightest mass per formula, and in particular the carbides, are the most promising anode material for lithium-ion batteries. And here you can see just a simple schematic having molybdenum-2 carbide as an anode. You can see that the fast ion intercalation and deintercalation can be achieved due to this 2D structure having suitable interlayer spacings. However, a major drawback for achieving the full potential of MaxENS as anode materials is their synthesis routes. So far, all of them, they are synthesized by following top-down synthesis routes, in particular chemical etching of their max phases. Here you can see the initial max phase. We chemically etch the intermediate metallic layers, and then we can have MXins after the lamination. However, this process results in an unavoidable byproduct of these residual surface terminations of functional groups. And of course, the long chemical etching process and the highest HF concentrations results in deterioration of the crystalline quality of the material by introducing many defects. So what is needed currently is to achieve direct bottom-up synthesis routes. So we can have MXins with clean surfaces without these surface termination groups and of better crystalline quality. So far, molybdenum-2 carbide is the only described MXin that has been synthesized by CVD. So the goal of our work is to further optimize the growth of molybdenum-2 carbide and basically achieve large-scale growth, which is also a big issue nowadays, because so far molybdenum carbide can be grown by CVD, but only in small flakes that they do not coalesce. And then we will continue to the growth of other carbides like titanium, chromium, and vanadium. So here you can see a simple schematic of the main steps of the CVD growth. Basically, we start by having a bilayer of two metals, a molybdenum substrate covered by a copper foil. We heat it up, so copper gets liquid, and then molybdenum atoms can diffuse through the melted copper and segregate at the surface. And then by introducing a carbon source that can be methane, for example, the segregated molybdenum on the surface reacts with carbon and creates the molybdenum carbide crystals. So this is how we started with CVD. This is how the two metallic foils were looking like before CVD, and after. You can see that the substrate, the molybdenum substrate, has been fully covered by the melted copper. And with SEM and EDX, we verified that we had this nice hexagonal formation of flakes. However, as I said in the beginning, in order to explore the potential of MXin, we can really need to understand their fundamentals. So we need to have in-depth scientific understanding of the growth mechanisms of MXins. And then when it comes for battery applications, we need to understand the lithium transport mechanisms. So this means that we need information on the atomic scale, and this can be achieved by scanning transmission electron microscopy. Here you can see a photo of our microscope in our lab. It is an FEI Titan, probe corrected and monochromated, and a simple schematic showing that we can use different detectors for imaging. We can collect electrons at very high angles, the so-called HADF imaging, so we can have pure Z contrast. And then we can also collect electrons scattered at lower angles, so we can have Z contrast and gradually only diffraction contrast. So we can, with ABF, for example, we can visualize at the same time both heavy and light elements. Of course, by combining spectroscopies, we can have chemical information by EDX, and even better with EELS, we can also have chemical information. EELS is more sensitive to the detection of light elements, and also we can have access to bonding information and to the electronic properties of materials. Furthermore, the lab is equipped with in situ holders and micro electromechanical chips, where we can expose our materials to precise heating, electrical biasing, and different gas environments. And of course, with the nanomachining capabilities of focused ion beam, we can miniaturize real-life devices and perform operando studies at the nanoscale. So, what is our goal for the in situ part of our work is to try to imitate the CVD process in situ in TEM and achieve growth of molybdenum to carbide, with a final goal to understand the very first stages of the growth mechanism. So this is how the chips look like. Here you can see that in one of the chips we have holes. These are the electron transparent areas where we will deposit our initial sample, and then the two chips, of course, create a closed cavity for the gases to be introduced. Here you can see step by step the whole process. We had this bilayer of molybdenum covered by copper. Here you can see SEM images. This is the cross-section view of this bilayer, copper and molybdenum. And then with FIB, we managed to extract a very thin lamella from the interfacial area. We polished down further, and then successfully we deposited with FIB this copper molybdenum bilayer on an e-chip. And then the important part of our study started. So practically we are talking about an in situ gas heating experiment imitating the CVD process. For people who are not familiar with in situ or generally with transmission electron microscopy, you can see that we can have and we can record videos basically of all monitors and recording live the whole process. So it is very interactive. We can introduce here the gases that we want, and then we can control precisely the temperature. We can go up to 1000 degrees, and we can also change the pressure of the inserted gases. We can go up to 1000 millibars. And at the same time, of course, we can see how these parameters affect our sample. So this is how our sample was looking like in the beginning. And then here we introduced a premixed gas of methane, our carbon source, with hydrogen. We started increasing the temperature and the pressure of the gas. We already see changes in our material, and gradually when we reached the maximum temperature and the maximum pressure of the gases, we see gradually the formation of these hexagonal, some of them were hexagonal at least, flakes. It is also important to notice that even at very high temperature, the system was quite stable, and we managed to have high resolution images. Here you can see that in one of the flakes, we can have crystalline information. We can see the lattice planes and have also information from the FFTs. So to cut the long story short, this is how the sample was before and after the in situ gas heating experiment. We managed to form hexagonal molybdenum to carbide flakes of good crystalline quality. And this was verified both by structural analysis, but also we verified with hills that molybdenum was indeed bonded with carbon. Here you can see the changes in the fine structure of the carbon peaks and the comparison between amorphous carbon and the carbon in the case of chemically etched commercial samples and the case of our bottom-up synthesized samples. So as I said also again, it is important to try to understand what are the atomistic factors governing the growth mechanism and to achieve a more controlled growth of layer by layer of enzymes. So with CVD, we started having different growth regimes. This happened by changing basically the relative thickness of the copper foils on top of the molybdenum foils. And most importantly, we introduced a holding step, meaning that we did a pre-annealing step of sorry, of our bilayers before we started the real growth process in order to give enough time for molybdenum to diffuse and reach the surface of the melted copper. So the final result was that we had these snowflake morphologies at the very first stages of growth, comprising segmented, stellar, and sectored plates. And we understood that this morphology happens because there are two growth modes taking place at the same time. We have a vertical growth mode that happens layer by layer, and a lateral growth mode, which is a growth edge to outwards stretching mode. Of course, the vertical growth happens in a slower way because the height itself poses a bulk diffusion barrier for molybdenum that prefers to move towards the edges. And so the lateral growth mode is faster than the vertical one. With respect to phase identification, combining HUD and annular bright field imaging was useful to basically tell the difference between the hexagonal and the orthorhombic structure. The orthorhombic structure is basically the ordered counterpart of the hexagonal. And what we found out was that carbon is ordered. You can see here that with HADF we can visualize only heavy elements, so we can see the molybdenum lattice, but with ABF we can visualize at the same time the molybdenum atoms, and in the middle the light atoms that are carbon. So they are creating a second sublattice being localized in the center of the molybdenum hexagonal closed-packed lattice. Of course, the ordered nature of our flakes was further verified by the superlattice reflections in the diffraction patterns. Let me check the time. Yeah, okay. Then we moved to the second part that deals with the fabrication of the micro-sized battery on a STEM chip. This is a very challenging part. Basically, so far only two groups have managed to show the assembly of a full all-solid-state battery on a chip and perform operando studies. So our goal was to manage to do that and then do the biasing study in order to understand the lithiation mechanism. Of course, understanding what happens at the interfaces is a major issue, and this is the main issue with respect to all solid-state batteries, basically. And of course, check the stability of all parts of the battery to see if we have decomposition or if we have defect formation. And of course, check the electrochemical performance of the battery itself. So this is a simple schematic of what we wanted to do. And the final goal, of course, is to compare a nano-sized battery using MXenes that are grown by us, so bottom-up grown MXenes in comparison to chemically etched MXenes. Here you can see step by step again what happened. We have SEM images from all three parts, the cathode, the electrolyte, and the MXene anode. And we started with FIB to deposit all different parts step by step. It is important also to see that we managed to hold all parts tightly together by using platinum, by depositing platinum during the FIB deposition. So this is the final result. Also, in order to achieve that, we took advantage of using the FIB optimized e-chips that do not have silicon nitride support film and give enough space for feeding to happen. This is a final STEM image showing that we had successfully managed to fabricate a micro-sized all-solid-state battery on a chip. You can see that all parts of the battery are like close together. The interfaces are good. We did, of course, an important step of a first pre-screening of the structural quality of all parts of the battery before we started the operando biasing experiment. So this is a work in progress. This is just the first attempt that we did so far. We exposed, we applied voltage to our battery, doing lithiation and delithiation processes, applying different voltages. Here you can see like a first example by going up to 2.5 volts. It was important that during many cycles, the battery was very stable. We didn't observe any deterioration of the interfaces. The only first observation that we made was with respect to the electrolyte itself. You can see that after many cycles, the electrolyte started decomposing. So let's say that the electrolyte so far seems to be the most sensitive part of the battery. And of course, on the MXenes side, we had many stacking faults. Also threading dislocations that seem to nucleate from some of the stacking faults. So far the material gives the impression that we have an increase of the defect density after the lithiation process, but we are working on that. And of course, a critical issue is to understand if these defects act as traps of lithium. So we perform EELs here to see if we have a clear signal of lithium and of higher concentration of lithium along the structural defects. So finalizing, I would like to thank all my colleagues and the funding team through the Norway grants, the GREG project. And this was a collaboration among the University of Oslo, the Structure Physics Group, the SINTEF industry in Oslo, and also the Port Institute in Wrocław in Poland. Thank you very much.